Well, take it on.
All right, thank you. Hi everyone. Thank you for the opportunity to present at this conference. Today, I'll talk about the work currently being done at Oak Ridge National Lab to support the Open MPI on Frontier Supercomputer. So first, I'd like to go over the agenda for this talk. I'll start by giving a high-level overview of the Frontier architecture and as far as it pertains to the work being done. I will give a description of the goals we're trying to achieve and the technical landscape we have to navigate. I'll then detail the solution I have selected and give an overview of the work which is taking place. I'll show some performance data we've collected so far and close with the current status of the project and the future plan that we have for the work to be done. So the Frontier Supercomputer is the first exascale computer with 4 Cray X supercomputer cabinets. Each Frontier node contains 1 optimized EPYC processor and 4 AMD Instinct accelerators for a total of more than 9,400 CPUs and more than 37,000 GPUs in the entire system. Let's dive a little bit more into what each node looks like. This is like I'm going to just cover the what pertains to this talk. Each Frontier compute node consists of 164-core optimized 3rd gen EPYC CPU with 2 hardware threads per physical CPU. It has access to 512 GB of DDR4 RAM memory. Each node also contains 4 AMD MI250Xs, each with 2 graphic compute dies. These are termed GCDs for a total of 8 GCDs per node. Each MI250X is connected to 1 HPE Slingshot 25 GB per second NIC for a total of 4 NICs per node. In terms of the MPI software stack, Frontier comes with the Cray MPI library and Libfabric. The Libfabric the CXI Libfabric provider, which is developed by HPE, allows Libfabric to use the HPE Slingshot NIC. So the Slingshot network utilizes HPC optimized Ethernet and uses a new NIC and switch infrastructure. HPE has developed the necessary kernel and system infrastructure for interfacing with the network, but the high-level MPI, which HPC applications typically use for inter-process communication, is currently limited to the Cray MPI implementation. This is a significant gap for the Frontier, and other large-scale DOE supercomputers, where the properties of the MPI play a significant role in the performance of the applications. To abate this issue, the project aims to develop and deploy GPU-aware Open MPI, an alternative MPI stack on Frontier. This would require integrating the CXI-enabled Libfabric with Open MPI and ensure functional and performance parity for both inter- and intra-node communication as compared to the Cray MPI software stack. So as we started our investigation into how to achieve this project goals, we identified 3 potential paths. The first one is to utilize the Open MPI MTL path, which primarily uses the tagged Libfabric APIs for both point-to-point and collectives. So here is a diagram, like a high-level diagram of what the 3 solutions look like. In this path, one provider is selected by the OFI MTL layer and used for all communication with both inter- and intra-node communication. This means in order to communicate over the Slingshot network, the OFI MTL layer will by necessity use the CXI provider. CXI providers does not implement shared memory communication. While it can be used for intra-node communication, it means traffic will need to egress and ingress the node. This will result in lower performance as we hit the bottlenecks of external communication. And it doesn't use the memory mechanism, the typical shared memory mechanism. The second option we thought about was to use the BTL path. This would use the Libfabric, RMA, and Atomic APIs. The BTL layer already has the ability to select the component to use based on the locality of the peer. the shared memory BTL component for intra-node communication, and the OFI BTL for inter-node communication. The final option we looked at was to use the UCX path. However, this would force us to integrate Libfabric in its entirety into the UCX library. Both these libraries are different designs, and the work needed to achieve the goal would be significant, although I see a UCX provider that was added to Libfabric recently. Sub option here is to just port the CXI provider functionality into the UCX library. We investigated all those paths, and we decided at the end to sort of focus on the Open MPI MTL path and the OFI and the BTL paths. The options, these two options provides us with the following advantages. It allows us to use CXI provider and leverage the development and testing that HPE has already done on the provider. It builds on already existing infrastructure in the Open MPI library. We don't have to build stuff from scratch. It pushes much of the functionality needed for supporting inter and intra-node communication in the Libfabric layer, which means that it would be useful for other middleware or applications which use Libfabric directly. Finally, it gives us the opportunity to contribute to the composability initiative within the Libfabric community, and I'll talk about that a little bit later. So what does the solution look like? For the rest of the talk, I'll focus on the MTL path. I'll not talk about the BTL path in a lot of details. Supporting Libfabric is already an Open MPI, so using the CXI provider was fairly trivial. It was just a matter of building Open MPI with a version of Libfabric that has the CXI provider. However, as mentioned earlier, the CXI provider does not have native support for shared memory. For that, we would need to modify the CXI provider or implement our own shared memory module, which would work in MTL or use the shared memory Libfabric provider that's already there. We determined to avoid making extensive changes to the CXI provider, as to this date it has not been upstreamed and is under development. So there will be a lot of conflicts if we try to modify the CXI provider. Implementing shared memory in CXI provider would also be redundant because we already have a shared memory provider that's implemented in Libfabric. Using the shared memory Libfabric provider, therefore, is the most logical approach. To use the shared memory provider, we thought of using a similar approach to the AWS IFA provider, use the same IFA provider approach that they did. However, this would have brought us back to making extensive changes to the CXI provider, which is something I wanted to avoid. Also, tightly coupling two providers is not a generic approach and would not have further benefit to the community. This line of investigation led me to considering a layered style provider which would link both the shared memory provider and the CXI provider. This approach would require minor changes to both providers, and this approach would also prove to be generic because it could theoretically be expanded to link multiple providers and even be used to implement multi-rail. I derived this approach of linking multiple providers from my past experiences in Lustre networking. At a very high level, LNet has a similar component design to Libfabric, where LNet acts as a generic networking layer on top of the Lustre network driver. Each Lustre network driver interfaces with a lower layer transport, such like TCP, IP, or verbs, and most recently Slingshot. LNet has the ability to simultaneously use multiple Lustre network drivers. So the approach there is to create a link provider, which we can use to link multiple providers together and be able to talk over multiple transports. Upon reaching out to the Intel Libfabric team, we discovered that they already have a design in place for peer APIs, which they talked about on Tuesday. The peer API design would aid in the design of the link provider. For the purpose of this project, we decided to focus on linking the CXI and shared memory providers using the link provider to start with. In essence, the LinkX provider will determine the locality of the process we're attempting to communicate with, and based on that, it will decide whether to use the shared memory provider or the CXI provider. So at this point, I'd like to pull up a sequence diagram that can sort of show how things work. So applications will initialize the MPI library. MPI library will request a list of providers from Libfabric. Libfabric will return a set of FI infos for each link. Right now, I use this syntax like shmem plus cxi colon link x. This is the current syntax I use to identify a link. However, we need to think how we will support linking an arbitrary set of providers in the future. This indicates the link that the links which MPI can select from. Open MPI will select the link provider. At this point, I'd like to detour and jump back to the frontier node architecture quickly here. So if we go back a couple of slides right here. At this point, I'd like to take a detour and jump back to the frontier node architecture. If you notice in this diagram, not all NICs are created equal. For example, if the MPI process is bound to core 3, it will be affine to HSN2, which would be the best interface for it to use. Selecting the optimal interface is critical for getting good performance. For this, we modified the Open MPI NIC selection algorithm to work based on distances. So in essence, it measures the distance between the process and the NIC and selects the nearest NIC. All right, I'll jump back to the sequence diagram here. Once Open MPI selects the optimal link, it will continue initializing LinkX providers. It opens the fabrics, the domains, endpoints, etc. LinkX will then create the CXI and shared memory provider fabrics and domains and endpoints. LinkX basically abstracts these two providers from the Open MPI layer such that OMP will only need to talk to one provider ever. This is where the peer APIs, which the Intel team presented on Tuesday, will kick in. LinkX will share its completion queues and receive queues with both the CXI and shared memory provider. Whenever the core provider completes a receive or a transmit request, it will post the completion in the LinkX shared completion queue. And whenever receive requests are made by the application, they are added to the LinkX shared receive queue. The CXI and shared memory provider will then look up and dequeue requests from there as messages arrive. It's worth noting there's a caveat here which the shared receive queues bring. It disallows the usage of offload tag matching. So if the hardware supports the offload tag matching, we can't use it if we're going through LinkX, so we have to switch it to software tag matching and get the provider to do the software tag matching. The basic problem here is with receiving from any peer case. If hardware tag matching is enabled, it is potentially possible for the same buffer to be used by both the CXI and shared memory providers to receive data in, causing data corruption. Getting back to the sequence diagram, Open MPI will ask LinkX for the address, for its address. LinkX will build the LinkX address by concatenating the addresses of all the endpoints it's linking. In our case, it will concatenate shared memory and CXI addresses and return that to Open MPI. Open MPI will then publish its address to the Modex database and then read the addresses of all the other peers, which should also be in LinkX address format. Open MPI will turn around and insert the peer addresses in the LinkX address vector table. LinkX will unpack the addresses and insert them into the appropriate provider. Note here that I haven't really looked into how we can use the shared address vector table approach, so this is something that I need to investigate a little bit. Once initialization is complete, the application can call the MPI data movement APIs, for example, MPI iSend. This will translate into Libfabric tagged APIs, which will end up in the LinkX provider. The LinkX provider will then look at the locality of the peer it's trying to communicate with and choose CXI or shared memory providers as appropriate. So as part of this work, we had to touch several areas in the shared memory provider. The changes done were in two categories: to add functionality which wasn't in the shared memory provider and improve performance, or try to bring the performance as close as possible to the Cray image, what Cray image gets. When we started the project, there was limited support for the ROCm HSA APIs. The primary problem there was that we didn't use the IPC protocol. This meant that data had to be copied from device buffers into a shared buffer, possibly segmented if it's too large, and then reassembled on the other end, and then copied back into the device buffers. This method provides pretty bad performance. The IPC protocol, on the other hand, allows an IPC handle, which references a device buffer to be shared from one process to another. The receiving process can then attach to this IPC handle and perform a direct copy from the remote device buffer into the local device buffer using the Rocker runtime HSA APIs. The IPC handle attach and detach procedures are fairly expensive operations, and it would be best to avoid having to do it on every operation. For this reason, I implemented the IPC caching mechanism to cache the IPC handles. Initially, I just kind of stole the UCX caching mechanism, but later it was changed to use the existing MR caching mechanism that's in Libfabric right now. To further optimize performance, I implemented the asynchronous copy operations. Rocker HSA APIs provide a method to trigger an asynchronous copy, which uses the device's DMA engine. Once the asynchronous operation is complete, a signal is flagged, which would trigger Libfabric to complete the operation. Another feature that we added was XPMEM support for Cray systems, XPMEM, and I think there is also an open source version of XPMEM, but for Cray systems, XPMEM provides a highly optimized method for sharing memory between processes. Shared memory at that time only supports CMA. Basically, XPMEM maps the remote process's virtual address space into the local address space, making the memory appear local to the process. This allows us to just mem copy directly. This comes with added benefit of being able to copy from XPMEM mapped memory to device memory directly. This allows more efficient host to device transfers. As far as I know, CMA doesn't have the same capability. I also have a couple of experimental features which I implemented. Likely we're not going to upstream those, but basically one is to only export certain regions using XPMEM instead of exporting the entire virtual address space of the process. And on the Rocker side, I implemented the AMD GPU support in Libfabric using HIP APIs. At this point, it was just intended as a reference implementation. Using HIP APIs end up using the Blit kernel for memory movement instead of the DMA engine on the GPUs. Although at the time of when I experimented with the Blit kernel, it performed a lot better because it used all the infinity fabric links between the GPUs. But the downside, it uses compute processing time on the GPU, which would potentially interfere with the computational workloads. So that's why we stayed away from the HIP APIs and focused on the HSA APIs. So I'd like to kind of move a little bit to the collective support that we did. We ran into a few performance issues when we started working on collectives. The two primary issues were the NIC selection, which I already discussed. We had to pick the most optimal NIC for communication per process. And the other thing that we worked on is to optimize shared memory the locking strategy used in shared memory. Up to this point, shared memory provider used the shared spin lock to lock the command passing and the entire memory operation. This would lead to serialization between the different processes. Therefore, the more processes you had running on the node, the less performant they became. So we moved away from this locking strategy to a lock-free strategy for command passing, which allowed the different processes to run more concurrently. Briefly, I'll touch on the one-sided support. One-sided and Open MPI goes through the BTL path. The Open MPI BTL layer has the ability to select between the Open MPI shared memory component and the OFI component depending on the peer locality. That said, I still wanted to be able to support BTL through the LinkX provider. The primary motivation behind this is to make sure that an application using one-sided point-to-point or collectives will not need to run Open MPI with different configurations. So once the provider is selected, LinkX is selected and it works for everything. For this, to get that working, I needed to implement the RMA and atomic APIs in LinkX, which up to this point, I only had worked with the tagged APIs because that's what the Open MPI MTL path used. One area I'm still kind of looking into is the memory registration and how we can best handle it in LinkX. There's some questions around that I'm sort of thinking through at this point. This is like a continuing effort. So in the next few slides, I'll just go over some of the preliminary data analysis that, the data collection that we did. There isn't a ton of it right now, sorry. But I'll just show that we are starting to get fairly comparable performance between Open MPI and Cray MPitch. So in this graph, for example, you can see this is just a point-to-point intranode for device to device, and you can see that the blue line here is Open MPI, and the orange line is Cray MPitch, and you can see that the performance is fairly close. We still need to focus a little bit on trying to see where the performance is lagging in some areas for some message sizes. This is another internode test results between D2D, like on the left-hand side is the D2D bidirectional bandwidth, and on the right-hand is the host-to-host, and you can see again, performance is fairly comparable. There's still some difference, but which we still need to investigate a little bit more. For all-to-all latency, for internode, we ran at 512 total number of processes with 8 processes per node on 64 nodes. And this is the sort of the result we got. You can see, again, that it's fairly comparable. There is a little bit of a spike in the Open MPI in the 4K range. But other than that, it's fairly close. We still need to sort of hone in to see what's going on with the performance. This is the broadcast, again, with 512 number of processes, 8 processes per node, and 64 nodes. So I'd like to go over a little bit of a status of the work. One thing actually I'd like to mention about before I leave the performance side of things. You don't see it on those graphs, but the small message performance in Open MPI is a little bit lower than Cray MPitch. So we need to understand why small messages don't perform as well. As the message size grows, we become more comparable, but we need to investigate why small messages are not working as well. There is some effort within the community to try to understand this a little bit more. So status of the project is currently the tag message support is in LinkX. I have implemented the shared completion and receive queues in both LinkX and CXI. Other features such as ROCm support, asynchronous, IPC, and XPMM are also completed to a large extent. The lock optimization and shared memory is done, and the Open MPI NIC selection based on distances is completed, sitting as a PR right now. Regarding the upstreaming efforts, a couple of things got upstreamed already, including the ROCm support and the optimization, the lock optimization shared memory. The next up is the XPMM work needs to get upstreamed as well, and then other bits and pieces which are needed to be upstreamed, and finally the LinkX will be upstreamed last. For future work, we will need to focus on collective performance improvement, including small message performance improvement. I need to complete the one-sided support. There's still some issues there that require further investigation. We need to complete the LinkX implementation for the rest of the Libfabric APIs before we decide to upstream, or we could probably upstream parts of it and add further support as we move along. This effort will likely include time spent in productizing LinkX as well, provider, the LinkX provider, and testing it by linking providers other than CXI and shared memory. Our primary focus has been to link CXI and shared memory, but we need to make sure that the provider is expandable to be in such a way that it's able to link any two providers which support shared receive queues or the peer APIs that were added. Another thing in our pipeline is to support Open MPI on the Aurora supercomputer, which uses the Intel GPU. I just got access to that, like a user system, and we're going to try to start looking into that. And as time permits, we're going to look at the multi-rail support via LinkX. This is something that we need to investigate further, and we want to see what workloads would benefit from that before sinking a lot of effort and time into it. And of course, all this stuff will need to get upstreamed eventually. Yeah, that's all I had for today. Thanks for your attention, and if there are any questions.
Kind of just a simple question. You said as time permits. Can you expand on that?
Well, it's that the work will really need to fit into ORNL's workloads. So if there are ORNL workloads which would benefit from multi-rail, well, then we'll spend more time into it. If there isn't, it will be more of a background project.
Got it. Okay. Makes sense. Thank you. Okay. Do we have any questions for this topic? Okay. I don't see any questions on chat. I don't want to rush anyone. I've done that before and someone pops up after I've called it. Does anyone have any questions? Okay, so we have apparently no other questions. Thank you. I appreciate the topic.
Thank you.